this video we will show how to simulate a millimeter scale inductor using the so-called H-phi formulation. The H-phi formulation allows to get much more accuracy with much less unknowns. It's therefore much faster to solve. So we create a new project where we import our step file for the magnetic inductor. There we have it. Now this requires an airbox around because it is 3D magnetics. So we will do some pre-processing. We'll draw a box that fits this inductor. There we go. Now we want to remove these extra pieces of coil that come out of the box. So we will ask for a fragment all operation to break the coil into what's inside the air and what's outside. Alright. Now we can apply the removal operation to remove this piece and that piece, only the part that is outside. And then we click confirm changes and our geometry is ready. Now that our geometry is ready, we can proceed to the material definition. So we will have an air box around, so we select the air material everywhere around. Then we'll select copper material. So for that we have to select the coil. Now for convenience, because there are a lot of pieces, we will just add the copper material and then we will pick all the volumes that are visible. And now, as a last step, we will select ferrite. So we could use a magnetic material with a nonlinear BH curve, but we will want to do here harmonic analysis for a given frequency. So we will use a linear non-conducting ferrite with a constant magnetic permeability. If we wanted to take into account nonlinear BH curve, we could do a transient or multi-harmonic simulation, which would be part of another video. So we could define, basically, since we don't have any ferrite predefined here, we could define just a non-conductive material, let's say air, that we can rename to ferrite. And then we will apply a given permeability here for the purpose of demonstration. We could take a relative 1000 permeability, and this is our ferrite region. Right, so what do we have? We have air around, we have copper, and we have a ferrite that is non-conducting but with 1000 relative permeability. Now we will add physics. So there we will define our, we could use a AV formulation, of course, this is quite standard, but we can also take advantage of the H-phi formulation. So it's like a H formulation, but in the non-conducting region you use the scalar potential phi, so this allows to really exactly take into account the fact that it's not conductor, so you don't need to use very small conductivity in the air. So let's go. We have the magnetism phi physics added. We have to say where it applies. So it is harmonic here, and we will say that it applies in the air and also in the non-conductive ferrite here. So all the non-conductive volumes. Then we will also add the H formulation, also harmonic, and this will apply in the conductor, so in this case the copper and this is harmonic as well. Now, we can couple them with the H-phi coupling. The intersection is automatically computed, nothing to select there. And then we can add, so you could add a constraint we will apply is a current source. So we will say we have, for example, 1 amp at the fundamental frequency, the real part that is applied. And then this is how we're going to apply it. So H-phi requires some care to apply the currents, but this is all fully automated in the graphical interface here. So you will provide the current supply by indicating where you want to have a given circulation. So you select the closed loop on the coil. If you zoom in, this will indicate you the orientation of the curve, and if you use the right hand rule, you will see that this will lead to a current of 1 amp at the fundamental frequency real part, and this amp is flowing inside that inlet phase. So this is all you needed to do to define the current source. And since there is only one conductor here, there's only one current source that needs to be defined. So this is enough in terms of physics definition. So we have the phi physics, the H physics in the conductors, H-phi coupling, and the current source here at the feed. Now we can go to the simulation settings. So we can run any number of simulations at the same time. You can even run different sweeps. There's a sweep on a given variable, and this will all run at the same time on the cloud. In this case, we just want to run one simulation. We will run it at 100 kilohertz. We will want to run it with domain decomposition to accelerate the simulation with, for example, 10 nodes and single core machines. That's it. So we first need to mesh. We will use our meshing algorithm that allows to refine the mesh where it's needed. So this will refine the mesh at the coil where the curvature is larger, and also between the turns because there are small air gaps in between, and this requires locally a smaller mesh. This is fully automatic and does the job nicely. Now it is worth mentioning that while this is running, well, we can already add the outputs that we want to see. So we want to see the magnetic flux density, for example, so real and imaginary part. If we just want to see the real part, then we remove the imaginary part, and we might want to see the current density. Also, we might, for example, just want to see the real part. How to compute inductances is also possible, but this will be part of another video. Now, while it is still meshing, we can have a look at the automatically generated script. This is fully tunable, and as you can see, everything is there. The entire H-phi formulation is defined here. If you want to automate anything or see any outputs, or for example in the scripting interface compute the inductance of what you're simulating, then you can easily do this in a one-liner post-processing. The meshing will be finished soon. Now the meshing is finished. We can preview it, and as you can see, the mesh has been really refined at the coil where you expect it to be refined. And this will be able to accurately capture the skin effects and proximity effects. Now, this simulation, we can run it. Now the simulation is finished, and we can visualize the results either in the browser or download the VTU files. Now we have selected to download the VTU files. Here's how we could visualize, for example, the current density. So it is the domain decomposition simulation, and so we have to first group all the pieces together with this trick of grouping the time steps. Now we want to see the current density J, and we could make a cut, for example, with a Z normal plane, and then we will be able to see that the skin effect and the proximity effect actually are taken into account.